Hello and welcome to our lab on momentum and energy. The lab is in two parts. For our first part, we have a flat track. Now this track is level, and on it are two carts. And I can determine the mass of these carts using a pan balance. And in fact, for this particular experiment, I'm going to make this cart a little more massive. Now I have a motion sensor down here. It can see this cart with the cell on it. And so as I move this cart, it can tell me the velocity of the cart. However, it doesn't know the velocity of this cart. This cart is invisible to the motion sensor. However, when I run this experiment, I'm going to run this, I'm going to make a collision of this cart with the heavier cart. And when I do that, they stick together. But continue to move down the track at a slower velocity than the initial cart. So let's sort of take a look at what we might predict the motion sensor would see when that happens. So let's imagine that we're making a graph of velocity versus time. So here's our velocity versus time graph. And so as that cart was moving down the track, pretty constant velocity, suddenly there's a collision. And now the two carts are moving together. Of course, it's still just seeing the one cart at a lower constant velocity. And so this first velocity, right before the collision, I'm going to call that, let's call that V initial. And the velocity just after the collision, let's call that V final. You'll be able to do this by inspecting your velocity versus time graph generated by the motion sensor. Now, we're going to talk about momentum here. Momentum, a P here, for momentum obviously, is equal to mv, mass times velocity. So the initial momentum of this entire system, now remember the second cart was initially stationary, so the entire momentum of the system before the collision was just this first rolling cart. Its mass, m1, times v initial. Now after the collision, you have two carts rolling. You have m1 times v final, that's the final momentum of that cart. It has lost momentum. However, the stationary cart, the heavier one, m2, has gained momentum. So it's moving also with the speed of v final, and it has a mass, m2. So you have two carts with this speed, and so you have, that's your momentum. The total mass of the carts times the speed. So hopefully, if the conservation of momentum law holds true, then through this collision, very few non-conservative forces at work, a little bit of friction in there, not a lot, but hopefully, to within a small amount of error, your initial momentum is equal to the final momentum because momentum is conserved. And so that's what we call the conservation of momentum. Now there's another thing we can look at, and that is this idea of impulse. Impulse obviously is J, and so that's equal to a change in momentum, delta P. And impulse is also related to force times time. That's also equal to force times time. Now the next thing I want to talk about is impulse. Impulse obviously is J, and that's equal to a change in momentum. It's also equal to, as it turns out, force, so the average force, times time, a change in time. And so when we had that collision, each of those carts underwent a force during the collision. There was an average force on the carts in the opposite directions. The stationary cart had a force that way. The rolling cart that hit the stationary cart had a force back that way. And Newton's third law says that those forces are equal in magnitude. And so if those two forces are equal in magnitude, and of course they experience the same delta T, the same time of collision because they're colliding with each other, then what that tells me is the change in momentum of the first cart has to equal in magnitude the change in momentum of the second cart. Delta P is going to be the same for each. So that tells me that this cart, it's going from V initial times M1 is its momentum, and it's dropping down to V final times M1. It's experiencing a change in momentum, delta P, which is the impulse. And so, however, the stationary cart is undergoing a positive change in momentum. It's going from zero momentum, being stationary, to having a momentum of m2 v final. Its momentum increases. Now, if Newton's law holds true, then the change in momentum of the first cart is equal in magnitude to the change in momentum of the second cart, just in the opposite direction. So that's impulse. Now, the last thing I want to analyze with this particular collision is energy. I think I mentioned before that momentum is conserved in a collision. However, energy is not. And so if you look at the kinetic energy, a potential energy of these carts really doesn't change. It's on a level track. However, if we look at the kinetic energy, we notice that from one side of the collision to the other, there seems to be a change in total kinetic energy. Before the collision, the total kinetic energy is just the kinetic energy of this first cart, which is 1/2 mv squared. This is m1 and v initial. After the collision, you've got the kinetic energy of those two carts that are stuck together. So you've got m2 plus m1 is the total mass, and then v final is the speed. So 1/2 total mass times v final squared. You find out that those two energies are not the same. There's been a decrease in the total kinetic energy, and therefore the total energy of this system. Energy has been lost to the surroundings. Part 2 of this laboratory includes the air table. Now, the air table is a flat table. It's leveled, and it has a smooth glass surface. And on top of the surface, we have a couple of layers of paper. First of all, some carbon paper under here that's electrically conductive, and then some regular old tracing paper here. And let me tell you what's going on with this. I have two pucks here that are going to float above this table. I can make a collision of two pucks. Now, these pucks are connected up here via these rubber hoses to the air supply. So air is pushed from this air tank down through the pucks and at the bottom, and they float on a little cushion of air. But then also in this tube is a conducting metal chain. And this metal chain is connected via these wires to this high voltage power supply. Now, this power supply is around 5,000 volts. And so it's a little bit dangerous. And so what I have is I have a safety device here. And so when I hold this down, then the voltage initiates. All right, and so that begins to spark. Now, this power supply is set to spark at 60 times every second. And so when I push this button, then 60 times every second, I'm going to generate a pulse of electricity, 5,000 volts, through the chains that are passing through these tubes. And so these chains that are at a high voltage difference between each other, that spark is going to jump through the paper, into the conducting paper underneath, across to the other puck, back up through the paper, and then back up the chain to the other side of the power supply. And so when that happens, 60 times a second, I'm getting a spark generated at the location of each of these pucks. And so if I pull this paper up, you can see that, I don't know if you can see it, but there's dots burning the paper. And so let me give you sort of an example of what it looks like. I'll turn this on. Pucks can then have a collision, just like that, or I can have one puck stationary like I did with the cart. And I can model this collision using this paper. Now, if we all did this, it would take forever and use a lot of paper. So what we have for you is sort of a pre-made experiment. And in this experiment, you can see there's a couple of tracks. First of all, we have mass 1 coming in over here. So the dots are far apart. That means it's moving pretty quickly. There's a collision, and then it moves away a different direction more slowly. The dots are closer together. Now, this is puck 2 sitting over here. It was stationary to begin with, but after the collision, then it began to move off this direction at a certain speed. Now, just like we saw in part 1 of the experiment, if we know the mass of each puck, like we do the mass of each cart, and that mass is given to you. And then using these dots, if we know that each dot is a 60th of a second, by measuring the distance between the first dot and the last dot, we have a distance. We know the time interval, each interval is 60th of a second, and so distance over time gives us the velocity of the puck. We can know the velocities of the puck before the collision and after the collision. Now the hard part is here, this collision is in 2 dimensions. When you have a collision in 2 dimensions, it's not as simple as the carts on the track where the collision is in one dimension. You have to look at the conservation of energy both in the x direction and in the y direction. Alright, so let's say we have a collision between 2 pucks. And the first puck comes in and then ricochets off this direction. And the second puck maybe goes up in that direction. It was previously stationary. And so you've got pretty much something that looks like that. And so the momentum before the collision, of course, is the momentum along that vector. The momentum after the collision is that puck plus that puck, 2 different pucks. Okay? And so momentum is a vector quantity. And so choose an axis. Well, I guess the most convenient would be maybe to choose this as your x-axis. And then all the initial momentum, of course, is in the x direction. So here's the initial momentum of the system. 1 puck in the x direction. Now after the collision, it's more difficult. You've got theta 1, let's pull this back, maybe theta 2. You've got 2 pucks going in different directions. And so you have to calculate these 2 vectors. What is the magnitude of the vector? It's the velocity. And what's the angle right here? And you add these 2 vectors together using vector addition to get the total vector momentum after the collision. So it's kind of mathematically involved. Now, we're going to compare magnitudes. So compare the magnitude of this initial momentum vector with the magnitude of this final, the sum of these 2 momentum vectors, and compare that using percent difference, because hopefully between these 2, initial and final, is not going to be much difference. There was a low friction table, right? An air puck is very low friction, so not many non-conservative forces at work. So hopefully momentum has been conserved before and after. But to determine it, you have to do vector addition. Now, what about conservation of energy? That hasn't been conserved. So if you look at the energy, 1/2 mv squared of the first puck, plus and compare that to the energy after the collision, which is 1/2 mv squared with this velocity, plus the second puck, 1/2 m2 v2 squared, that velocity. Add those 2 kinetic energies together. If energy has been lost, then the sum of those 2 energies won't be as much as that initial kinetic energy of this first puck. So hopefully you should be able to show that even though energy is not conserved, energy being a scalar quantity, it's not a vector, the vector momentum before and after the collision has been conserved. So that's sort of the purpose of the air table experiment.